All right, I have another fun, silly little application. Here's yet another party decoration. It's this nice bell shape. And of course you can get this bell shape by, it came flat and you unfurl it like that. So the question is, how is this different than the previous problem? So think about this 3D shape. How is it different than the previous problem we had? So let me kind of trace it here. World's best drawing of half a flattened bell, right? So we'll come back to that in a sec. Let's think about that truck headlight again. We were considering the volume of the interior, which we would have to flood with inert gas or something. But you're also going to have to pay for the plastic or the glass on the exterior, on the support structure. So let's think about the support structure. For the headlight, which had the inner curve 3 root x. So I'm going to draw a big old axis here. And we've got that curve like before. But now let's say the support structure goes all the way up to there. So here's 10 centimeters. This was what, 3 root 10. So now I care about taking this region and rotating that around the x-axis. So can I approximate the area with disks anymore? That's what I did before. We had a disk that fit kind of nicely in here, right? And we imagined what's the volume of that disk. But now I don't care about that disk so much. I care about the area, or the volume of something that starts kind of up here and gets spun around like this. And I just happen to have the world's best visual aid. So that's the area we care about, right? Not just the part in front of the page, but also the part that would go in back of the page. So what's the volume of this thing? Imagine if it's completed all the way around there. So what's the volume of this differential element? It's also called a washer. Let's try that again. Let me go get a washer. So this is what a washer usually looks like if you buy it at the hardware store. It's the same basic concept. In this case, it's bigger and shinier. What is the volume of a washer? Well, a washer is a disk with the disk in the middle taken out, right? So we could say it's pi times the outer radius squared times dx. So that's the volume of the entire disk. Imagine, ignore this hole in the middle. Minus pi times the inner radius, the part that you're imagining taken out, squared times dx. And you could simplify that a little bit. So you'd get what? Pi times outer radius squared minus inner radius squared times dx. Is that what you would get? Or would you get pi times outer radius minus inner radius squared dx? Which one of those two lines do you think is correct, or are they the same? Well, it turns out they're not the same, and this one is not correct. So we're going to cross that out. We're going to say to this one, Yes. You can't just collect the squaring across a subtraction like that, right? That would make life a lot easier, but it ends up being wrong. So if that's the area of my outer, that's the volume of my differential element, then I just have to add up all the differential elements the same way we did on the other one. So it would be the integral a to b pi times the outer radius function of x squared minus the inner radius function of x squared dx. So you could give names to these like f and g. I would always have trouble remembering what's f and what's g. So just think of them using long words like inner radius function and outer radius function. So what is our inner radius function here? That was the same function we had before. What's the outer radius? What is the outer radius of the support structure here and here and here and here? Well, it's just always that horizontal line, right? Which is at a distance of 3 root 10 from what I'm spinning around. So that outer radius function here, let's see, I'm integrating 0 to 10, right? Pi times the outer radius function of x doesn't even involve an x, it's just 3 root 10 squared. And then the inner radius function was 3 root x squared dx. And is that going to be a hard integral to do? Well, just like before, mathematicians tend to choose things when they can where things will just cancel and give you a polynomial. This is just a constant. You don't even have to do the power rule because it's just some constant. It's what, 3 squared times 10. So again, it's just a polynomial integration. All right. Oh, we forgot to connect it back to our first problem. What's going on here? When I spin this around, I'm going to have this kind of hollow part, right? So I could imagine a disc for this part, or a washer for this part spinning around, and then I'd also have another disc in here. So it's this kind of non-convex shape would make life difficult, so we're not actually going to do it, but that's the difference between this shape and this shape together, and the previous example where we were spinning a convex region around that touched the axis everywhere, so we didn't have a hole in the middle. So overall, we're in chapter 7.2, we're integrating volumes of rotation by using disks if there's no hole in the middle, or washers if there is a hole in the middle. In some sense, they're really both washers. It's just the disks have a washer inner radius of 0, and so we just don't even bother to write this term. It's just all outer radius. So you can think of it that way if you want, or you can think of it as two separate formulas.